Picture this: you're floating in the vast emptiness of space, closer to a black hole than any human has ever dared to go. The darkness around you isn't just empty, it's alive with the pull of something so powerful, it warps the very fabric of reality. Time itself slows down, minutes stretch into hours, hours into years. A single orbit around this cosmic monster could mean decades pass for everyone you've ever known back on Earth. This isn't just science fiction, it's the mind-bending reality of time dilation near black holes, a phenomenon so strange it feels ripped straight from the pages of Interstellar. Black holes are more than just cosmic vacuum cleaners, they're nature's ultimate time machines. Get close enough and gravity doesn't just bend light, it twists time. Think about that for a second. The same force that keeps your feet on the ground becomes so intense near a black hole that it alters the flow of time itself. Astronauts orbiting Earth age slightly slower than people on the ground, a tiny effect, but proof that gravity and time are deeply linked. Now amplify that by a factor of millions. Near the edge of a black hole, time doesn't just crawl, it nearly stops. What feels like seconds to you could be centuries for someone watching from afar. It's one of the most bizarre consequences of Einstein's theory of relativity, and yet it's real. But why should you care? Because this isn't just about far-off celestial oddities, it's about understanding the universe's most extreme limits. Time dilation near black holes forces us to rethink everything we know about reality. Could we ever harness this effect? Could a black hole be a gateway to the distant future? Or is it just a one-way trip into the unknown? Over the next few minutes, we're diving deep into the science behind these questions, unraveling the mysteries of time, gravity, and the cosmic giants that rewrite the rules of existence. Buckle up, because by the end of this journey, you'll never look at time the same way again. To understand why black holes warp time, we need to start with Einstein's groundbreaking idea, the theory of relativity. Imagine time isn't some universal clock ticking at the same speed everywhere. Instead, think of it like a river flowing at different speeds depending on where you are. The stronger gravity's grip, the slower time moves. Satellites orbiting Earth actually experience this every day. The clocks on GPS satellites run slightly faster than those on the ground because they're farther from Earth's gravity. If engineers didn't account for this tiny time shift, your navigation apps would be off by miles within minutes. Now take that same principle and crank it up to cosmic extremes. Near a black hole, gravity isn't just strong, it's overwhelming. The closer you get, the more space-time bends, stretching seconds into eternities from an outsider's perspective. Picture two identical clocks, one placed near a black hole's edge, the other safely far away. The first clock might tick just once while the other ticks 1,000 times. This isn't an illusion, time itself is being reshaped. To wrap your head around this, think of space-time as a trampoline. Place a bowling ball in the center, that's your black hole. Now roll a marble near the dent, it spirals inward, just like how objects fall toward the black hole's pull. But here's the twist: the deeper the dent, the slower time moves for anything near it. For someone watching from the trampoline's edge, your movements would appear frozen, even if you felt like everything was normal. That's relativity in action, time and space woven together, bending under the weight of gravity's mightiest monsters. Black holes are cosmic enigmas born from the death throes of massive stars. When a star many times larger than our sun burns through its fuel, it doesn't just fade away. It collapses under its own gravity in a cataclysmic explosion called a supernova. What remains is a core so dense, so unimaginably compact, that not even light can escape its pull. That's the moment a black hole is born. At its heart lies the singularity, a point where matter is crushed into infinite density, warping space-time into a bottomless pit. Surrounding it is the event horizon, the point of no return. Think of it like a cosmic toll booth. Once you cross, there's no turning back. The gravity here is so fierce that escape would require moving faster than light, which, as far as we know, is impossible. But what makes black holes truly mind-bending is how they defy everyday logic. Take their size, for example. A black hole with the mass of our Sun would be just 6 kilometers across, smaller than a city. Yet its gravitational grip would extend far beyond that, bending the paths of stars and devouring anything unlucky enough to wander too close, and some black holes are anything but small. Supermassive ones, weighing millions or even billions of times our Sun's mass, lurk at the centers of galaxies, shaping their very evolution. To grasp their power, picture tossing a rock into a pond. The ripples spread outward just like gravity's influence, but near a black hole, the pond becomes a whirlpool. Space-time itself spirals inward, dragging everything with it. Planets, gas, even other stars can vanish into the darkness, fueling the black hole's hunger. Yet despite their destructive reputation, black holes aren't cosmic vacuum cleaners randomly sucking up the universe. They obey the same gravitational rules as any other object, just cranked up to extremes. If our Sun were magically replaced by a black hole of the same mass, Earth would continue orbiting as usual, just in perpetual night. Understanding black holes means confronting the limits of physics. They're where Einstein's relativity and quantum mechanics collide, where space and time cease to behave as we know them. And while we can't see them directly, their presence is betrayed by their effects, the way they bend light, distort orbits, and even emit faint whispers of radiation as they slowly evaporate over eons. They're not just dead stars, they're portals to the universe's deepest mysteries. Gravity doesn't just hold the universe together, it controls time itself. To see how, let's start with something familiar: Earth. Stand on the ground and gravity tugs at you with a force so ordinary you don't even notice it. But even here, time moves slightly slower at your feet than it does at the top of a skyscraper. The difference is minuscule, a few nanoseconds over a lifetime, but it's real. Atomic clocks precise enough to measure this prove that gravity's grip, however gentle, literally drags on time. Now imagine amplifying that effect. Near a black hole, gravity isn't just a gentle tug, it's a cosmic sledgehammer. Space-time isn't merely bent, it's stretched like taffy, warping time so dramatically that clocks near the event horizon tick at a glacial pace compared to those farther away. This isn't a quirk of measurement, it's the universe's rulebook playing out in extremes. Einstein called it gravitational time dilation, and black holes are its ultimate showcase. A fun way to visualize this is to think of space-time as a grid of stretched rubber. Place a bowling ball Earth on it, and the grid dips slightly. Roll a marble, a passing satellite, and its path curves gently. But swap the bowling ball for a wrecking ball, a black hole, and the grid stretches into a funnel. Now time isn't just bent, it's stretched thin near the bottom where gravity's pull is strongest. A clock placed there would tick slower than one at the rim, not because it's broken, but because time itself has slowed down. This gets even wilder when you consider how black holes warp perception. Imagine two astronauts, one orbits safely far away while the other drifts toward the event horizon. To the distant observer, their partner's movements become sluggish, like a video stuck in slow motion. Their signals stretch into deeper and deeper red shifts, their final approach seeming to freeze at the edge. But for the doomed astronaut, time feels normal. Their watch ticks steadily, their heartbeat stays regular until, of course, gravity's tidal forces take over. This paradox isn't a glitch, it's relativity in action, revealing how time is fluid, not fixed. What's truly astonishing is that we've observed this effect just on a smaller scale. Take the star S2 whipping around the supermassive black hole at our galaxy's core. As it nears the point of closest approach, its light stretches to redder wavelengths, a telltale sign of time crawling under intense gravity. It's a cosmic confirmation that Einstein was right. Gravity doesn't just bend space, it twists time into knots. So why does this happen? At its core, time dilation is a trade-off between energy and perception. In high gravity, you're fighting against spacetime's curvature, and that struggle steals energy from time itself. It's like climbing an endless hill. Your every second costs more effort, so time outside seems to rush ahead while you're left behind. Near a black hole, the hill becomes a cliff, and the effect becomes inescapable. This isn't just theoretical spectacle, it reshapes how we see the universe. If time is malleable, then the cosmos isn't a static stage but a dynamic fabric woven by gravity's hands. Black holes are the looms where spacetime's threads are pulled tightest, revealing patterns we're only beginning to decode. And while we might never dive into one, their extreme nature lights the way to understanding time's true nature, not as a constant but as gravity's silent, shifting shadow. Let's take one of the most famous thought experiments in physics, the twin paradox, and give it a black hole twist. You've probably heard the classic version. One twin stays on Earth while the other rockets off into space at near light speed, only to return younger than their sibling. But swap that spaceship for a black hole, and the effect becomes so extreme it borders on the surreal. Picture two identical twins, let's call them Alex and Sam. Alex volunteers for a daring mission, orbiting just outside a black hole's event horizon, close enough to feel time's brutal slowdown. Sam, meanwhile, watches from a safe distance. For Alex, time passes normally, heartbeat steady, breaths even, but for Sam, something eerie unfolds. Alex's movements slow to a crawl. A single hour for Alex stretches into years for Sam. By the time Alex returns after what feels like a week, Sam might have aged decades. This isn't just theoretical drama. Time dilation near a black hole is gravity's ultimate flex. The closer you get, the harder spacetime pulls on time itself. At the event horizon, the stretching becomes infinite. Time, from an outsider's view, grinds to a halt. That's why some call it the frozen star effect. To distant observers, anything falling in seems to hover forever at the edge, never quite crossing over, like a video frame stuck on pause. Yet for the person actually experiencing it, time flows normally until gravity's tidal forces well. Let's just say physics gets messy. What's wild is that this isn't science fiction. We've seen hints of this time warp with objects like SGRA, the supermassive black hole at our galaxy's center. Stars orbiting it show measurable delays in their light, stretched by gravity's grip. It's as if the universe itself is proving Einstein right in real time. Now, here's where it gets even stranger. If Alex could somehow hover just above the event horizon, say, with some futuristic propulsion, and then return, the reunion would be a one-way trip to the future. Earth might be unrecognizable, civilizations risen and fallen, all while Alex experienced mere days. It's the ultimate time capsule, no machine required, just gravity's raw power bending the rules of existence. But here's the haunting question. What does this mean for someone falling in? From their perspective, time flows normally. They'd cross the event horizon without fanfare, unaware of the cosmic slowdown others witness. Yet to the outside universe, their final moments stretch into eternity. It's a chilling reminder that time isn't just a universal ticker, it's a shape-shifter molded by gravity's invisible hands. So the next time you glance at a clock, remember, it's not just counting seconds, it's measuring your place in spacetime's ever-shifting landscape, a landscape where black holes twist time into knots and the universe plays by rules far stranger than fiction. The event horizon isn't just the boundary of a black hole, it's the edge of reality as we understand it. Cross this invisible threshold and the laws of physics as we know them cease to apply. But what makes this point so chillingly unique isn't just the one-way ticket to oblivion, it's the way time itself seems to freeze from the perspective of someone watching from safety. Imagine you're observing a spacecraft drifting toward a black hole. As it nears the event horizon, something bizarre happens. The ship's clock, visible through a powerful telescope, ticks slower and slower. Its final approach stretches into eternity, the image growing dimmer and redder as light struggles to escape the black hole's pull. The ship never quite seems to cross the horizon, it just fades into a frozen, ghostly silhouette. Yet, for the astronauts inside, time flows normally. They'd cross the threshold unaware of the cosmic drama unfolding for distant observers. This paradox cuts to the heart of relativity's strangest predictions. Time dilation near a black hole isn't an illusion, it's a fundamental reshaping of reality based on perspective. The event horizon isn't a physical barrier, it's a point where gravity warps space-time so severely that even light can't climb out. And because light carries information about time, the moment an object's light can no longer reach you is the moment its time appears to stop from your vantage point. But here's where physics gets twisty. If time freezes at the horizon, how does anything ever actually fall in? The answer lies in the nature of observation. From outside, the infalling object's light takes infinitely long to reach you, its final signal stretched to imperceptibility. Yet for the object itself, crossing happens in finite time. This mismatch isn't a flaw in the math, it's proof that time isn't universal. It's personal, shaped by where you are and how gravity pulls at you. The implications unsettle even seasoned physicists. Take Hawking radiation, the faint glow predicted to leak from black holes. Quantum mechanics suggests particle pairs popping into existence near the horizon could lead to one escaping while the other falls in. But if time is frozen at the boundary, how does this process even occur? The paradox hints at deeper mysteries, like whether the event horizon is truly where we think it is or if quantum effects blur its edges. This tension between relativity and quantum mechanics isn't just academic, it's a battleground for understanding spacetime's true nature. Some theories propose firewalls of energy at the horizon, annihilating anything that crosses. Others suggest information about what falls in gets smeared across the surface like a hologram. Each idea strains our intuition, forcing us to confront whether black holes are cosmic shredders or gateways to something stranger. What's certain is this: the event horizon isn't just a line in the sand. It's a mirror held up to the universe, reflecting how little we truly grasp about time, gravity, and the fabric of existence. The closer we look, the more questions arise, and that's what makes these cosmic monsters endlessly fascinating. They're not just destroyers, they're the universe's most brutal teachers, revealing the limits of our knowledge with every paradox they conjure. Gravity's grip near a black hole doesn't just slow time, it tears reality apart, and nowhere is this more visceral than in the gruesome phenomenon of spaghettification. Imagine drifting feet first toward a black hole's event horizon. At first, the pull on your toes is slightly stronger than the pull on your head, a tiny difference but enough to start stretching you like taffy. As you get closer, that gentle tug becomes a violent rip. Your body elongates, thinning into a human noodle, atoms straining against forces so strong they overwhelm the bonds holding you together. But here's the twist: this isn't just a physical stretching, it's a warping of time itself, where every inch of your body experiences time at a drastically different rate. Spaghettification happens because black holes don't just have gravity, they have gravity gradients. Think of it like standing in the ocean. At first, the water laps evenly at your ankles. But as a tidal wave approaches, the difference in force between your feet and your head becomes extreme. Near a black hole, space-time itself is the wave, and it's crashing down on you with unimaginable ferocity. The result: time doesn't just slow uniformly, it fractures. Your feet, closer to the black hole, experience time crawling while your head, just meters away, ticks relatively faster. It's as if your body becomes a living time capsule, each part aging at a different speed. This isn't just theoretical horror, it's a direct consequence of Einstein's relativity. Time dilation isn't a blanket effect, it's granular, varying millimeter by millimeter when gravity's pull is this extreme. For an astronaut falling in, the sensation would be surreal. Their feet would seem to freeze in place, muscles responding sluggishly as signals from their brain struggle to traverse the stretched space-time. Their last moments would be a grotesque dance of distorted time and space, a reminder that gravity isn't just a force, it's a sculptor reshaping reality itself. To visualize this, picture a rubber band marked with dots. Normally, if you stretch it, the dots move apart evenly. But near a black hole, it's like pinning one end of the band to a wall and yanking the other end with infinite force. The dots near the wall barely move while those at the far end skyrocket away. Now replace those dots with moments in time. Your feet are the pinned end, trapped in slow motion while your head races forward. This is the nightmare of tidal forces, not just tearing you apart but fragmenting your very experience of time. What's eerie is how this mirrors the black hole's own anatomy. Just as space-time stretches infinitely at the event horizon from an outsider's view, your body's stretching becomes infinite from your own perspective, if you could survive long enough to notice. The atoms in your feet inch toward oblivion, their time nearly halted while your head's atoms rush onward. It's a fitting metaphor for black holes themselves, not just objects but cosmic whirlpools where time and space spiral into chaos. And here's the cosmic irony: while spaghettification is lethal, it's also a glimpse into the universe's deepest symmetries. The same forces that stretch your body also stretch light into unrecognizable wavelengths, bending photons into a last distorted scream before vanishing. This is why black holes don't just consume matter, they unravel it strand by strand, second by fractured second. So the next time you hear about time dilation near a black hole, remember, it's not just about clocks slowing down. It's about the universe itself twisting into a funhouse mirror where gravity's pull doesn't just bend time, it shatters it. And in that violent fragmentation lies a brutal truth: near a black hole, even time isn't safe from the stretch. Standing at a safe distance, watching someone fall toward a black hole would be like witnessing a cosmic horror in slow motion, an eerie ballet of physics unraveling in real time. As the doomed traveler inches closer to the event horizon, their movements grow sluggish, their gestures stretching into agonizing slowness. Every second they experience is stretched into years from your perspective, as if the universe itself is pressing pause on their final moments. Their spaceship, once gleaming under starlight, dims to a dull crimson, its light redshifted stretched to longer, redder wavelengths as it fights against gravity's relentless pull. The closer they get, the fainter their signal becomes, like a radio station fading into static, until at last they hover motionless at the horizon's edge, a ghostly silhouette frozen in time. This surreal spectacle isn't just an illusion, it's gravity's ultimate magic trick. Light escaping from near the event horizon has to climb out of a deep well of warped spacetime, sapping its energy in the process. Each photon loses strength, shifting from visible light to infrared, then to imperceptible radio waves, until finally nothing escapes at all. To you, the observer, your companion never truly vanishes. They linger at the threshold, eternally suspended in their last moment, a fossil of light imprinted on the fabric of spacetime. Yet here's the cruel twist: while their image seems frozen from your vantage point, their own experience is horrifyingly different. For them, time flows normally, no slowdown, no hesitation. They cross the horizon unaware of the cosmic drama unfolding for those left behind. It's a chilling reminder that reality isn't just what happens, it's also where and how you witness it. Two perspectives, both true, separated by the brutal physics of relativity. This paradox isn't just theoretical. Astronomers have glimpsed echoes of this effect in the wild. Take the supermassive black hole at the center of our galaxy. Sagittarius A, stars orbiting it show measurable time delays, their light stretching and redshifting as they swing close to the abyss. It's nature's own experiment, confirming Einstein's predictions with terrifying precision. But the most haunting question remains: if time appears to freeze at the horizon, does anything ever truly fall in? The answer lies in the limits of observation. From your distant perch, the infalling object's last signal takes forever to reach you, stretched thinner and thinner until it's indistinguishable from the black hole's dark embrace. But from the object's perspective, the plunge happens in finite time. This disconnect isn't a flaw, it's proof that time isn't absolute. It's a shape-shifter bending to gravity's will, leaving us to grapple with a universe where even the simplest acts like falling become riddles written in light and shadow. So the next time you gaze at the night sky, remember, black holes aren't just voids, they're cosmic theaters staging relativity's greatest performances, where time bends, light falters, and the universe reveals its most unsettling truths. For the person falling into a black hole, reality unfolds in a way that defies the frozen tableau witnessed by outside observers. While distant watchers see time grind to a halt at the event horizon, the falling astronaut experiences no such slowdown. Their watch ticks steadily, their breath comes at the same rhythm. The crossing feels startlingly mundane, no flashing lights, no sudden jolts, just the inexorable pull of gravity growing stronger with every passing second. Picture this from inside the spacecraft. The instruments might scream warnings about tidal forces or gravitational stresses, but the flow of time itself remains eerily normal. If you could glance out the window, stars wouldn't freeze, they'd streak past as you accelerate, their light blue shifting ahead of you and reddening behind. The black hole's silhouette grows, swallowing more of your view until the universe seems to contract into a shrinking circle of light. Yet until the final moments, nothing about your personal timeline feels extraordinary. Here's where relativity's paradox becomes visceral. To an outside observer, your last moments are stretched across eternity. But for you, the event horizon isn't a wall or a barrier. It's just another point in space you pass through, like crossing an invisible county line. There's no marker, no sudden shift, only the growing realization that no force in the universe could now propel you back. This disconnect isn't just philosophical, it reshapes how we understand causality. Imagine shouting a final message to your crew as you cross the horizon. From your perspective, the words leave your lips and travel outward at the speed of light. But outside, those sound waves or radio signals are stretched to infinite wavelengths, their energy drained by gravity's grip. What you intended as a farewell becomes, for everyone else, a silence that never quite arrives. The brutal poetry of this moment lies in its asymmetry. Two truths coexist. For you, time marches forward. For the universe you leave behind, your story ends in frozen stasis. This isn't an illusion, it's relativity's ruthless arithmetic. Gravity doesn't just bend light, it warps the very meaning of now. And then comes the final, silent revelation. As space-time curves ever more steeply around you, the universe's entire history might seem to flash by. Not as a hallucination, but as light from distant stars, accelerated by the black hole's distortion, finally reaching your eyes. Galaxies that hadn't yet formed when you began your fall might appear to age and die in seconds. It's as if the cosmos itself is playing its greatest hits on fast forward, a farewell gift from the fabric of space-time. Yet this spectacle isn't without grim irony. The same forces that offer this cosmic highlight reel are also tearing you apart atom by atom. Time flows normally for you, but space is bent to its breaking point. Your last coherent thought might be realizing that, somewhere out there, your loved ones are watching your final moment forever. To them, you're still reaching toward the horizon, frozen in time's amber. But you've already crossed into the dark. Could humanity ever harness the time-warping power of black holes, turning these cosmic monsters into tools? The idea isn't as far-fetched as it sounds, at least on paper. Imagine a civilization advanced enough to park a spacecraft just outside a black hole's event horizon where time crawls. While centuries pass across the galaxy, the crew inside experiences mere months. Suddenly, interstellar travel isn't limited by human lifespans. You could cross the cosmos, arrive in the distant future, and witness the evolution of stars or the rise and fall of civilizations, all while barely aging a day. It's the ultimate time capsule, no wormholes required, but the obstacles are as colossal as the black holes themselves. First, there's the matter of survivability. Even if you could withstand the tidal forces, hovering near the horizon would require propulsion beyond anything we've dreamed of. Think engines harnessing the energy of stars just to counteract gravity's pull. Then there's the communication problem. Signals sent from the ship would redshift into oblivion, making real-time contact with the outside universe impossible. You'd truly be cut off, a prisoner of relativity's grip. Another tantalizing idea, energy extraction. Black holes aren't just gravity wells, they're cosmic power plants. Theoreticians like Roger Penrose have proposed wild schemes like the Penrose process, where objects split near a rotating black hole could steal energy from its spin. Picture a spacecraft firing a capsule into the black hole's ergosphere, the region just outside the horizon where spacetime itself is dragged into a whirlpool-like rotation. If the capsule splits in two, one fragment might plunge in, while the other escapes with more energy than it entered with. It's like robbing a bank where the vault is made of twisted spacetime. Yet even this faces jaw-dropping challenges. The energy gains would be microscopic unless you're dealing with supermassive black holes, and the precision required makes splitting atoms look like child's play. Not to mention the raw materials you'd need to haul payloads across light years just to feed the beast. Perhaps the most surreal possibility is using black holes as quantum computers. Their event horizons could act as natural information scramblers, a feature that might one day help crack problems impossible for classical machines. But this hinges on theories we can't yet test, like holographic principle, where all the information falling into a black hole is somehow encoded on its surface. For now, these ideas lie squarely in the realm of speculation, brilliant thought experiments highlighting how far we've yet to go. But they also underscore something profound. Black holes aren't just destroyers. They're cosmic puzzles, and each solution we tease out reshapes our understanding of physics itself. The day we even begin taming their power might be the day we stop being a planetary species and truly become children of the stars. Time travel has long been the stuff of science fiction until you factor in black holes. These cosmic anomalies don't just bend time, they twist it into knots so tight they might just loop back on themselves. The key lies in a bizarre feature of Einstein's equations, closed time-like curves. Picture a racetrack where the finish line is also the starting point, a path through spacetime that circles back to its own beginning. Near a rotating black hole, gravity's drag on spacetime could theoretically create such a loop, allowing you to travel back to your own past without breaking any laws of physics. But before you start drafting letters to your younger self, there's a catch. The universe has a built-in safeguard, the Novikov self-consistency principle. This idea states that any time travel scenario must remain logically consistent, no grandfather paradoxes, no changing history. If you tried to go back and prevent your own birth, the universe would conspire to stop you, like a cosmic bouncer ensuring the timeline stays intact. It's not that time travel is impossible, it's that the universe won't let you break its rules. Take the infamous kill Hitler dilemma. According to Novikov, any attempt to alter a pivotal historical event would fail. Your gun might jam, or you'd miss the train to Vienna. The past isn't a sandbox, it's a locked puzzle where every piece already fits. Some physicists argue this principle makes closed time-like curves eerily sterile. You could witness history but never rewrite it. Others counter that even observation alone would ripple through causality in ways we can't yet predict. The wild card in all this, rotating black holes, also known as Kerr black holes. Unlike their static cousins, these spin so fast they drag spacetime around them like taffy, creating a gravitational vortex where closed time-like curves might form just outside the event horizon. Enter such a whirlpool and you could in theory emerge in your own past, but here's the rub. Surviving the journey would require speeds and energies far beyond our reach, not to mention navigating a maze of tidal forces that could shred atoms. And then there's the ultimate irony. Even if you succeeded, you'd likely find time travel as futile as it is fascinating. The Novikov principle suggests a paradoxical comfort. The universe might already account for your meddling, weaving your actions into the timeline so seamlessly that you were always meant to intervene. Your past self, hearing footsteps in the dark, might turn just in time to see you completing a loop that was never broken. So are black holes time machines. The math says maybe, reality says not yet, but the mere possibility cracks open a window into Einstein's universe, one where time isn't an arrow but a labyrinth, and black holes are the doors we're still learning to unlock. Movies love to dramatize black holes, but how much of what we see on screen is grounded in real science? Take Interstellar, a film praised for its scientific ambition. The portrayal of the black hole gargantua was so meticulously crafted. Physicist Kip Thorne worked closely with the visual effects team to ensure its swirling accretion disk and gravitational lensing matched Einstein's equations. The result, a stunningly accurate depiction of how light bends around a black hole, warping the background stars into a flickering halo. Even the time dilation on Miller's planet, a waterlogged world where 1 hour equals 7 years back on Earth, was based on real physics. The filmmakers didn't just guess, they calculated the gravitational time dilation that would occur near a supermassive black hole spinning at near light speed. But Hollywood still takes liberties. Interstellar's crew survives extreme tidal forces that would, in reality, shred a planet, let alone a human, long before time dilation became an issue. And while the film's Tesseract sequence inside the black hole is visually mesmerizing, it ventures deep into speculative territory. Realistically, crossing the event horizon isn't a gateway to a fifth-dimensional bookshelf. It's a one-way trip to spaghettification. Other films aren't as careful. In Event Horizon, black holes become portals to literal hell, ignoring physics entirely for horror's sake. Even The Black Hole, a Disney film from the 1970s, depicted the phenomenon as a swirling tunnel with a fiery core, more fantasy than astrophysics. These creative choices are entertaining but blur the line between science and fiction, leaving audiences wondering what's possible and what's pure spectacle. The best sci-fi strikes a balance. Interstellar's time dilation scenes nail the emotional weight of relativity, the heartbreak of Cooper watching his children age decades in minutes. That's the real power of black holes, not just their ability to warp space-time, but to warp human lives. The movie's mix of accuracy and artistic license reminds us that while black holes are cosmic monsters, they're also mirrors, reflecting our hunger to explore, even when the universe defies our expectations. So next time you see a black hole on screen, ask yourself, is this science or poetry? The answer's usually both, and that's what makes them endlessly compelling. Black holes aren't just gravity's masterpiece, they're also quantum enigmas, where the universe's largest and smallest laws collide. Take Hawking radiation, the faint glow predicted to leak from black holes. It emerges from the chaotic dance of quantum particles near the event horizon, where empty space isn't truly empty. Quantum mechanics tells us that particle-antiparticle pairs constantly flicker in and out of existence. Normally, they annihilate instantly, but near a black hole, one particle might fall in while the other escapes, stealing a tiny bit of the black hole's energy in the process. Over eons, this trickle could evaporate even the mightiest black hole, a cosmic contradiction where the densest objects in existence slowly fade like morning fog. Now, here's where time dilation twists the quantum story. As particles escape, their perception of time differs wildly based on their position. A photon emitted just outside the horizon experiences extreme time dilation. It might take millennia to reach an observer far away, stretched by gravity's grip. Yet from the photon's perspective, its journey is instantaneous. This mismatch isn't just a curiosity, it hints at a deeper truth. Time near a black hole isn't just warped, it's fractured, with quantum processes playing out differently depending on whose clock you're watching. The implications get stranger when you consider virtual particles. These fleeting quantum fluctuations usually vanish without a trace, but near the event horizon, they become real, their existence cemented by the black hole's gravitational divide. The escaping particles carry information energy stolen from the black hole's mass. Over trillions of years, this slow bleed could transform a black hole from a cosmic titan into a whisper of radiation. It's a paradox. The same gravity that bends time into knots also seeds the black hole's eventual demise. What does this mean for time perception? Imagine two quantum particles created at the horizon. One falls in, the other escapes. The escaping particle's clock ticks normally as it flees, but the infalling particle's time grinds to a halt from an outsider's view. Yet quantum entanglement suggests these particles remain mysteriously linked, their fates intertwined across spacetime. This creates a bizarre scenario where quantum mechanics and relativity wage a silent war over what now even means. Hawking radiation also forces us to confront black holes' most haunting question: what happens to information swallowed by the abyss? Quantum physics insists information can't be destroyed, but black holes seem to erase it utterly. The resolution might lie in how time and quantum states interact at the horizon. Some theories suggest information isn't lost, it's scrambled and encoded in Hawking radiation, like a cosmic hard drive reformatting itself. Others propose holographic principles, where everything falling in gets imprinted on the horizon's surface, a two-dimensional archive of three-dimensional events. This quantum time tango isn't just theoretical. Lab experiments with analogs like dumb holes in supercooled fluids mimic event horizons, letting scientists study Hawking radiation in miniature. These experiments reveal something profound. Quantum effects near boundaries aren't unique to black holes. They're universal features of extreme physics, appearing anywhere spacetime gets stretched to its limits. So next time you picture a black hole, don't just think of it as a vacuum cleaner for stars. See it as a quantum clock, ticking slower on the outside while particles perform their subatomic ballet within. It's where time doesn't just bend, it shatters into a kaleidoscope of perspectives, each revealing a new layer of the universe's deepest mysteries. If black holes are the universe's cosmic drains, sucking everything into their infinite darkness, then white holes are their hypothetical opposites, cosmic fountains, spewing out matter and energy in a relentless explosion. The math of general relativity allows for these bizarre objects, though we've never seen one. Unlike their black hole cousins, white holes can't be entered, they only expel. Anything approaching a white hole's event horizon would be violently repelled, as if spacetime itself were pushing back. But here's where it gets wild. Some theories suggest white holes could be black holes in reverse, not just in space but in time. Picture a film reel running backward. A black hole's crushing singularity becomes a white hole's erupting birth. Matter that vanished beyond the event horizon now re-emerges pristine and untouched, as if the universe hit rewind. This symmetry is more than poetic. It's embedded in Einstein's equations, which treat time as a dimension that could, under extreme conditions, flow in either direction. For a moment, ignore the practicalities and consider the implication. If white holes exist, they might be black holes playing the cosmic tape in reverse, with time itself flipped like an hourglass turned upside down. But could time truly run backward near a white hole? The laws of thermodynamics say entropy, the universe's tendency toward disorder, always increases. Yet white holes defy this. They'd require conditions where entropy decreases, ejecting ordered matter into chaos. Some physicists argue this makes them impossible, or at least staggeringly unstable. Others speculate they might exist only fleetingly, a brief spark of reversed time before collapsing back into equilibrium. Imagine a firework exploding in reverse flames rushing inward, debris reassembling into a pristine shell. That's the dreamlike physics of a white hole where cause and effect might dance to a different rhythm. There's another tantalizing idea. White holes could be the other end of black hole tunnels. In this view, black holes don't lead to oblivion, they're cosmic shortcuts with white holes as the exits. Matter swallowed here emerges there, perhaps in another universe or another time. It's a seductive thought, but the reality is thornier. The same forces that stretch time near a black hole's horizon would likely collapse any tunnel, known as a wormhole, before anything could traverse it. Quantum effects might stabilize such a passage, but only with exotic matter possessing negative energy, something we've never observed. What would you see if you stumbled upon a white hole? Unlike a black hole's ominous darkness, a white hole would likely blaze with radiation, its expelled matter colliding violently with the surrounding universe. Some theories even suggest the Big Bang itself could have been a white hole event, a singular eruption of space-time and energy. It's a humbling thought that the birth of our cosmos might mirror the death throes of a black hole in some other reality. Yet for all their theoretical intrigue, white holes remain phantoms. No astronomical observation has ever confirmed one, and many scientists suspect they're mathematical curiosities rather than physical realities. But that's the beauty of cosmic speculation. It forces us to confront the limits of our understanding. If time can stretch and warp near black holes, who's to say it can't reverse elsewhere? The universe loves symmetry, and white holes offer a haunting glimpse of what that symmetry might look like. A universe where endings are beginnings, where time's arrow isn't fixed, and where the fabric of reality might just be more flexible than we ever dared to dream. If black holes bend time and white holes potentially reverse it, then wormholes might just be the universe's ultimate cheat code, cosmic shortcuts where space and time fold like a piece of paper, letting you leap across the galaxy or even through the ages in a single step. The idea isn't pure fantasy. Einstein's equations actually allow for these hypothetical tunnels, known as traversable wormholes, which could connect two distant points in spacetime. Picture a hallway between stars where one door opens near Earth and the other dumps you out near Alpha Centauri, or maybe even in a different century. But here's the catch: wormholes are terrifyingly unstable. The moment one forms, it would likely snap shut faster than you could say. Paradox, crushed by its own gravitational forces. To stay open long enough for anything to pass through, a wormhole would need scaffolding made of exotic matter, something with negative energy that repels gravity rather than attracts it. We've never found such a substance, and the closest we've come is observing weird quantum effects like the Casimir force, where empty space itself seems to push objects together. That's a far cry from the cosmic duct tape needed to prop open a spacetime tunnel. The time travel potential is even thornier. Theoretical models suggest that if you could stabilize a wormhole, one mouth could be placed near a black hole or accelerated to near light speed, slowing time relative to the other end. Step through and you'd emerge in the past or future, depending on how the exits are configured. But this isn't just engineering on an impossible scale, it's a recipe for causality violations. What happens if you trip through a wormhole and prevent your own birth? The universe might retaliate with quantum feedback, collapsing the tunnel in a burst of lethal radiation. Even if wormholes exist naturally, they'd likely be microscopic, flickering in and out of existence at the quantum level. Scaling one up to human size would require energies comparable to twisting an entire star into a pretzel. And then there's the navigation problem. Without a map, you might step into a wormhole only to exit inside a supernova or the core of a neutron star, cosmic roulette with the worst odds imaginable. Still, the math keeps physicists intrigued. Some theories suggest wormholes could be hiding inside black holes disguised by singularities. Others propose they're entangled across dimensions like quantum particles whispering across the multiverse. It's a reminder that the universe's wildest possibilities often lurk at the edges of what's plausible. Wormholes may never be more than pencil scratches on a physicist's notepad, but they prove one thing. When it comes to space-time, the universe has a flair for the dramatic. While black holes are the undisputed champions of time dilation, they aren't the only cosmic heavyweights bending the rules of time. Take neutron stars, the collapsed cores of dead stars so dense a single teaspoon would weigh 1 billion tons on Earth. Their gravity isn't as extreme as a black hole's, but it's still strong enough to warp time measurably. Picture a clock placed on the surface of a neutron star. From a spaceship orbiting safely above, that clock would tick noticeably slower, perhaps losing a few hours over a year compared to the ship's time. That might not sound dramatic, but consider this. GPS satellites orbiting Earth have to account for time differences measured in microseconds. Near a neutron star, the effect is thousands of times stronger, proving relativity isn't just a black hole party trick. It's universal. Then there are quasars, the blazing hearts of distant galaxies powered by supermassive black holes. These cosmic lighthouses shoot out jets of energy moving at nearly light speed, creating their own subtle time warps. Gas swirling around the central black hole heats up to millions of degrees, emitting light that fights against gravity's grip as it escapes. From our vantage point, that light is redshifted, stretched to longer wavelengths, but it's also a testament to time dilation in action. The photons we detect from quasars have been climbing out of deep gravitational wells for billions of years, their energy sapped by the relentless pull of spacetime. When we observe them, we're seeing the universe's history through a lens of stretched time. Even white dwarfs, the fading embers of stars like our Sun, show hints of this phenomenon. These dense stellar corpses pack the mass of a star into a sphere the size of Earth, creating gravity fields strong enough to subtly slow time. The effect is tiny compared to black holes, but it's there. Consider Sirius B, the white dwarf companion to the brightest star in our night sky. If you could stand on its scorching surface and survive the 400,000-degree heat, your watch would tick slower than one on Earth by about 90 seconds every century. Not exactly a time machine, but a reminder that relativity never takes a day off. The real surprise, even our own planet plays the time-warping game. Earth's gravity, as gentle as it feels, slows time at sea level compared to the top of Mount Everest. The difference is vanishingly small, just a few nanoseconds per year, but it's measurable. Atomic clocks precise enough to detect this prove that time dilation isn't just for exotic celestial objects. It's woven into the fabric of spacetime itself, from the mightiest black hole to the peaks of our tallest mountains. What ties all these phenomena together is gravity's universal grip. Whether it's the crushing weight of a neutron star or the whisper soft pull of Earth, every object with mass bends spacetime to some degree. Black holes might twist time into knots, but they're just the most extreme members of a cosmic family where time is always relative. So the next time you glance at the stars, remember, out there, time dances to gravity's tune, sometimes a waltz, sometimes a head-spinning tango, but never, ever ticking the same way twice. Einstein's theory of relativity might sound like abstract math, but we've actually tested it here on Earth, and the results are just as mind-bending as anything near a black hole. Take atomic clocks, the most precise timekeepers ever built. In one famous experiment, scientists placed identical clocks on airplanes and flew them around the world while comparing them to clocks on the ground. The result, the airborne clocks ran slightly faster, gaining a few nanoseconds. That tiny difference proved something extraordinary. Time literally moves slower the stronger gravity's grip. The clocks on the ground, closer to Earth's mass, lagged behind their high-flying counterparts, just as relativity predicts. But the real kicker came from space. GPS satellites orbiting Earth have to account for time dilation every second. Without corrections, their clocks would drift off by about 38 microseconds per day, enough to throw your navigation apps off by kilometers. That's relativity in your smartphone, silently adjusting for the fact that time ticks faster in orbit than on your driveway. So why can't we test black hole-level time dilation directly? The challenge isn't just distance, it's survival. Near a black hole's event horizon, time slows so dramatically that minutes stretch into years elsewhere. But getting close enough to measure this would mean contending with forces that shred matter atom by atom. Even robotic probes wouldn't last long enough to send back data. And the signals they did manage to transmit, they'd redshift into oblivion, stretched by gravity until they're indistinguishable from background noise. That hasn't stopped astronomers from finding clever workarounds. Watch a star orbit the supermassive black hole at our galaxy's center, and you'll see its light redshift as it swings close, then blue shift as it speeds away. That's not just a Doppler effect, it's gravity tugging on time itself, making the star's clock appear to slow during its closest approach. We're essentially witnessing relativity in action from 26,000 light-years away. For now, black hole time dilation remains just out of reach, a tantalizing shadow on the edge of our instruments. But every atomic clock on a plane, every GPS correction, and every redshifted star whispers the same truth: Einstein was right. Time isn't fixed, it's fluid, bending under gravity's weight, waiting for us to stretch our understanding further. Black holes don't just bend time, they threaten to erase the very fabric of reality as we know it. This crisis, known as the information paradox, pits Einstein's relativity against quantum mechanics in a battle over whether black holes are cosmic shredders or secret archivists. Here's the heart of the conflict. Quantum physics insists that information, the fundamental details of every particle state, can never be destroyed, yet black holes appear to vaporize everything they swallow, leaving no trace behind. Even time, which normally marches forward with clockwork predictability, becomes entangled in this mystery, warped beyond recognition at the event horizon. Imagine tossing a book into a fire. In theory, if you knew the exact position and energy of every flame and ash particle, you could reverse engineer the book's contents. But toss that same book into a black hole and the rules change. According to relativity, the book's information vanishes forever, crushed into the singularity. Yet quantum mechanics screams otherwise. Particles are linked by entanglement, their states interdependent no matter how far apart they are. If the information inside the black hole is truly lost, it would unravel quantum theory's core principle, that the universe preserves causality at every scale. Hawking radiation complicates things further. As black holes slowly leak energy, they evaporate over eons. But what happens to the information of all the matter they've consumed? Does it vanish when the black hole dies, or is it somehow encoded in the radiation, like a cosmic last will and testament? The answer could redefine how we understand time itself. If information escapes, it implies a hidden structure to spacetime, a way for data to survive even when time seems to stop at the horizon. Some physicists propose wild solutions like the holographic principle. Picture a black hole's event horizon as a two-dimensional surface where all swallowed information gets smeared like ink on a page. From the outside, the black hole becomes a hologram, its contents projected onto the horizon surface. Time here isn't linear, it's fragmented, with every moment stored like frames on a film strip. Others suggest walls of searing energy at the horizon that instantly incinerate anything crossing, preserving information by converting it into pure energy. But here's the twist. Both ideas clash with relativity's prediction that crossing the horizon should feel uneventful, with no fiery barrier or sudden stop. Time dilation near the horizon means an infalling observer would perceive nothing unusual, just empty space, while an outside watcher sees them frozen forever. This disconnect isn't just philosophical, it's a rift in physics itself, exposing how little we grasp about time's true nature under extreme conditions. The paradox even bleeds into quantum entanglement. Imagine a particle pair split at the horizon. One falls in, the other escapes. Their entangled states should, in theory, link the black hole's interior to the outside universe. But if the interior is forever cut off by the horizon, does that entanglement somehow encode the lost information? Recent theories like ER=EPR propose that black holes might be connected to their Hawking radiation via hidden wormholes, threading the needle between relativity and quantum mechanics. What's at stake isn't just theoretical neatness. If black holes truly destroy information, they rewrite the rules of cause and effect, making the universe's history unknowable. Time becomes a fractured mirror with pieces missing. But if information survives hidden in Hawking radiation or holograms, it hints at a deeper layer of reality, where space-time is woven from quantum threads we've yet to untangle. For now, the paradox stands, a reminder that black holes aren't just cosmic curiosities. They're the universe's most ruthless teachers, forcing us to confront the uncomfortable truth. Our best theories of time and reality might be incomplete, waiting for the next Einstein to reconcile the irreconcilable. As we peer into the cosmos' distant future, black holes emerge not just as time-warping curiosities, but as the universe's final timekeepers. Picture a reality trillions of years from now, long after the last stars have flickered out. The cosmos drifts toward heat death, a state where entropy maxes out and energy spreads so thin that no work can be done. But amid this frigid stillness, black holes linger, their gravitational grip still warping time in slow, silent defiance. These cosmic relics could become the last meaningful markers of time's passage in an otherwise timeless void. Consider the slow-motion demise of black holes themselves. Through Hawking radiation, they evaporate over incomprehensible timescales, small ones vanishing in bursts of particles over billions of years, while supermassive giants take longer than the current age of the universe to fade. As they shrink, their time dilation effects intensify. A black hole in its death throes might seem frozen to an outside observer, its final moments stretched across eons. Yet for the hole itself, evaporation happens in a finite, albeit mind-bendingly long time frame. This asymmetry creates a bizarre chronology where the universe's last events play out in extreme slow motion, like the final frames of a film stuck in an endless loop. The implications get stranger when you factor in civilizations, or their remnants trying to survive in this far future era. Hypothetical beings huddled around a dying black hole could use its time dilation as a cosmic lifeboat. By orbiting near the horizon, they might stretch their subjective seconds into external millennia, effectively outlasting the rest of the universe's decay. But it's a grim trade-off. Resources would be non-existent, and any energy extracted would come at the cost of hastening the black hole's evaporation. Their existence would become a battle against entropy itself, fought in a space-time arena where time's flow is their only leverage. Even black holes' eventual disappearance hints at time's malleability. As they evaporate, their gravitational hold weakens, and the dramatic time warps near their horizons soften. The last surviving observers might witness the universe's final ironies, time dilation fading as the last structures capable of bending it wink out of existence. Without black holes, the cosmos reaches a state where time becomes uniform and featureless, no gravity wells left to twist it, no events left to measure it. Time, in effect, loses all meaning. This bleak vision isn't just speculative fiction, it's rooted in our best understanding of thermodynamics and relativity. Black holes are the universe's ultimate hourglasses, their slow decay counting down toward a future where even time itself may become irrelevant. Yet in their paradoxes, their ability to stretch moments into eternities while hurtling toward their own oblivion, they offer a haunting reminder. The cosmos isn't just a stage for matter and energy. It's a tapestry where time is woven by gravity's hand, and black holes are the loom's final, stubborn threads. So while heat death might seem like an end, black holes suggest it's more of a transformation, a universe where time doesn't stop so much as dissolve, leaving behind a silence so profound that not even a tick remains. Floating near a black hole isn't just dangerous, it's a one-way ticket to the universe's most violent shredder. The moment you stray too close, gravity's tidal forces take over, stretching your body like cosmic taffy in a process gruesomely nicknamed spaghettification. Picture this: your feet, just centimeters closer to the black hole, feel a stronger pull than your head. At first, it's a faint tug, but as you descend, the difference becomes drastic. Muscles strain, bones snap, and atoms themselves are ripped apart. Even a stellar mass black hole would turn you into a human noodle long before you reach the event horizon. It's not just sci-fi gore, it's the unavoidable consequence of gravity's gradient, where every inch of your body experiences a radically different pull. But tides aren't the only hazard. Black holes are surrounded by swirling disks of superheated gas and debris, blazing with X-rays and gamma rays powerful enough to cook you instantly. These accretion disks, often hotter than the cores of stars, emit lethal radiation that would fry electronics and DNA alike. Then there's the high-energy particle jets, spewing matter at near light speed. Getting caught in one would be like standing in the beam of a cosmic particle accelerator, bombarded with enough energy to vaporize a spacecraft. Could futuristic technology ever make this survivable? Hypothetically, yes, but the engineering hurdles border on fantasy. First, you'd need a shield capable of withstanding temperatures measured in millions of degrees and radiation levels that dwarf Chernobyl. Materials like graphene or hypothetical metastable alloys might offer a sliver of hope, but even they would falter under prolonged exposure. Then there's propulsion. To hover near the event horizon without falling in, your engine would need to counterbalance gravity's pull, equivalent to harnessing the energy output of a star just to stay in place. Even antimatter reactors, the most efficient power source we can imagine, would struggle to meet that demand. But let's say you crack the energy problem. Communication becomes the next nightmare. Signals sent back home would redshift into oblivion, stretched by gravity until they're undetectable. You'd be utterly cut off, a silent voyeur at the edge of oblivion. And time dilation, that's the cruelest twist. While you might experience minutes near the horizon, years or centuries could pass for everyone else. Surviving the trip is one thing, returning to a familiar universe is another. There's a grim irony here. The same time-warping effects that make black holes potential time machines also render them practically unreachable. The universe seems to guard these cosmic anomalies with layers of lethal physics, as if daring us to test the limits of our ingenuity. For now, black holes remain the ultimate look but don't touch phenomena. A reminder that some frontiers are better explored through math and imagination than with flesh and steel. Time dilation near black holes doesn't just bend physics, it warps the very foundations of human thought, forcing religion and philosophy to grapple with questions that feel ripped from ancient myths. Imagine a monk meditating near a black hole's event horizon, where minutes stretch into centuries for the outside world. By the time they return, their teachings might be relics of a forgotten era, their spiritual insights buried under millennia of cultural change. This isn't just a sci-fi scenario, it's a modern twist on age-old dilemmas about mortality and eternity. Religions have long envisioned timeless realms, heaven, nirvana, or the afterlife where earthly constraints dissolve. But black holes offer a tangible, if terrifying, version of such places. Regions where time crawls so slowly that a human lifespan could span cosmic epochs. The implications unsettle even fundamental ideas about consciousness and divinity. If a soul or mind could survive the tidal forces, would it experience time differently than matter? Eastern philosophies like Buddhism, with their emphasis on the illusion of linear time, find eerie parallels in relativity's fluid clock. Meanwhile, Abrahamic traditions might wrestle with the paradox of free will under extreme dilation. Could a prayer uttered near the horizon echo across millennia, or would God's perception transcend spacetime's bends? These aren't abstract musings, they're pressure tests for doctrines built on fixed notions of cause and effect. Reality itself becomes fluid in these thought experiments. Hindu cosmology speaks of cyclical universes where creation and destruction repeat in vast loops. A black hole's singularity, where physics breaks down, mirrors the primal void of traditions like the Tao Te Ching, a state beyond time and form. Even atheist philosophies confront existential whiplash. If time is this malleable, what anchors human purpose? Existentialists like Sartre argued meaning is forged through action, but how does that hold when actions near a black hole stretch into obscurity? The most haunting question lingers at the intersection of science and spirituality. Does time dilation make immortality possible? Not in the magical sense, but as a grim logistical feat. A civilization orbiting a black hole could, in theory, stretch subjective moments into cosmic eras, watching stars die from the safety of slowed time. But at what cost? Isolation, the loss of connection to anything beyond the horizon. These are Faustian bargains that mirror myths of cursed eternal life. The Greek gods punished mortals who sought immortality without eternal youth. Black holes impose a similar catch, offering extended time at the price of irrelevance. Perhaps the deepest lesson lies in humility. For millennia, humans have framed time as a river or arrow, measurable and predictable. Black holes laugh at such simplicity. They force us to confront time as something wild and viscous, a substance that thickens and thins under gravity's whim. Mystics and physicists alike might agree, reality's fabric is far stranger than any scripture or equation could fully capture. And in that shared awe, science and spirituality find rare common ground, kneeling together at the edge of the unknowable. Science fiction has long used black hole time dilation as a narrative time machine, bending plots in ways only relativity could justify. Take Carl Sagan's Contact, where the protagonist, Ellie Arroway, plunges through a wormhole network crafted by an ancient alien civilization. The journey lasts mere hours for her, but back on Earth, decades vanish in her absence. Sagan didn't just pluck this idea from thin air, he consulted physicist Kip Thorne to ensure the math held up. The result, a haunting portrayal of cosmic isolation, where the universe moves on without you, and returning home means confronting a world that's aged beyond recognition. It's not just a plot device, it's a meditation on loss framed by the cold equations of space-time. Joe Haldeman's The Forever War takes this concept to the battlefield. Soldiers fighting interstellar wars near black holes experience months while centuries pass on Earth. The time dilation becomes a metaphor for the dislocation of war. Veterans return to a society so altered, they're relics in their own timelines. Haldeman, a Vietnam veteran, infused the novel with the visceral alienation he felt coming home to a changed America. The black hole isn't just a setting, it's a mirror for the psychological chasm between soldier and civilian, where time itself becomes the enemy. Then there's Interstellar's literary cousin, Diaspora by Greg Eban. Here, post-human civilizations use time dilation near black holes as a strategic pause button, slowing their perception of time to outlast cosmic threats. While the novel leans harder into speculative territory, it echoes a terrifyingly plausible reality. For a species facing extinction, black holes could be the ultimate bunkers, trading the flow of time for survival. These stories share a common thread. Time dilation isn't just a scientific quirk. It's a narrative scalpel dissecting human themes of loneliness, change, and resilience. When Ellie Arroway steps out of the wormhole to find her world moved on without her, or when Haldeman's soldiers become strangers in their own future, the science serves the story, not the other way around. But sci-fi also warns of time dilation's darker uses. Alastair Reynolds' Revelation space series features the light huggers, starships skirting black holes to manipulate time for tactical advantage. Entire battles are fought across subjective minutes that span objective millennia, turning warfare into a grotesque game of temporal chess. The message is clear. In the wrong hands, time dilation isn't just a curiosity, it's a weapon fracturing societies across unbridgeable gulfs of time. What makes these explorations so compelling is their grounding in real physics. Authors like Sagan and Haldeman didn't treat relativity as magic. They let its rules shape their worlds, giving their stories an authenticity that resonates long after the last page. Whether it's the existential dread of returning to a forgotten future or the strategic hunger to control time itself, black hole dilation in sci-fi isn't about escapism. It's about holding a funhouse mirror to the human condition, where the universe's coldest laws reveal our warmest fears and hopes. The next frontier in unraveling black hole time dilation isn't just theoretical. It's being built right now in labs and launch facilities around the world. Take the Laser Interferometer Space Antenna, or LISA, a revolutionary mission set to launch in the 2030s. Unlike ground-based observatories, LISA will consist of 3 spacecraft flying in a precise triangle, 2.5 million kilometers apart, connected by lasers. This cosmic measuring tape will detect gravitational waves, ripples in space-time caused by collisions between black holes and neutron stars. But here's the game changer. LISA sensitivity could let us hear the subtle distortions caused by time dilation near these objects. Imagine capturing the moment a star spiraling into a black hole slows to a crawl from our perspective, its final orbit stretched by relativity into a low-frequency hum. It's like tuning into the universe's most dramatic slow-motion replay. Then there's the Event Horizon Telescope, the global network that brought us the first image of a black hole's shadow in 2019. Future upgrades aim to capture real-time footage of matter swirling around Sagittarius A, our galaxy's supermassive black hole. By tracking blobs of plasma in the accretion disk, astronomers hope to measure time dilation directly, watching as these bright spots redshift and slow near the event horizon, like cosmic clocks ticking at half speed. Combined with AI-driven analysis, these observations could reveal how space-time warps under conditions no lab could ever replicate. But the holy grail might lie in quantum sensors. Researchers are developing atomic clocks so precise they could detect minute time variations caused by Earth's gravity, or if placed on a deep space probe near a black hole. Picture a spacecraft equipped with these clocks orbiting just outside the event horizon. Data beamed back, though heavily redshifted, could show time's flow altering in ways that reveal the black hole's spin, mass, and even hidden quantum effects at the horizon. It's a long shot, but projects like NASA's Atomic Clock Ensemble in space are already proving the concept in Earth orbit. The most daring proposals sound straight out of sci-fi. Breakthrough Starshot, for instance, envisions sending gram-scale probes to Alpha Centauri using laser-powered sails. Adapt that tech to a black hole mission, and we might fling ultra-lightweight sensors toward Sagittarius A, sacrificing them to capture milliseconds of data as they're torn apart. Grim, maybe, but the payoff could be unprecedented measurements of time dilation in the death throes of spacetime itself. What ties these projects together is ambition, not just to observe black holes, but to interrogate them. Every new telescope, every quantum sensor is a step toward answering the big questions. How does time truly behave at the edge of oblivion? Can we reconcile relativity with quantum mechanics? And what secrets lie in the dark hearts of these cosmic titans? The tools we're building today might not just unlock black holes, they could redefine our understanding of reality itself. Black holes have been mythologized as cosmic vacuum cleaners, relentlessly sucking in everything around them. But that's not how they actually work. Gravity near a black hole is intense, sure, but it behaves just like gravity anywhere else in the universe. Think of it this way: if you swapped our sun with a black hole of the same mass, Earth's orbit wouldn't change. The planets would keep circling, oblivious to the darkness at the center, because the gravitational pull depends on mass, not whether that mass is a blazing star or a collapsed singularity. The only difference, eternal night, another stubborn myth that black holes are holes at all. They're not empty spaces, they're unfathomably dense objects, packing the mass of entire stars into a volume smaller than a city. The event horizon isn't a physical surface, it's just the point where gravity becomes too strong for light to escape. Cross it, and you're not falling through a tunnel, you're plunging into a maelstrom of warped space-time, where the laws of physics as we know them start to unravel. And then there's the Hollywood trope that black holes are interdimensional portals or gateways to other universes. While wormholes, hypothetical shortcuts through space-time, are mathematically possible, no evidence suggests black holes function this way. The reality is far bleaker. Anything crossing the event horizon is crushed toward the singularity, where tidal forces stretch atoms into oblivion. Time might slow to a crawl from an outsider's perspective, but for the unlucky traveler, it's a one-way trip to Spaghetti Town. Perhaps the most persistent misconception is that black holes are rare, distant monsters. In truth, they're everywhere. Our galaxy alone harbors millions of stellar mass black holes, ghosts of dead stars, and nearly every large galaxy centers on a supermassive one. Even stranger, tiny primordial black holes might lurk unseen, relics of the early universe's violent birth. They're not just cosmic oddities, they're fundamental threads in the fabric of space-time. So why do these myths persist? Because black holes defy intuition. They twist light, fracture time, and challenge the very notion of reality. But stripping away the fiction reveals something even more extraordinary. A universe where gravity's rulebook bends but never breaks, and where the truth is stranger and more fascinating than any sci-fi plot. From stretched seconds to frozen eternities, black holes don't just bend time, they shatter our understanding of it entirely. We've journeyed through the mind-bending reality where gravity's grip turns minutes into millennia, where falling into the abyss means watching the universe age without you, and where the very fabric of causality frays at the edges. These cosmic monsters challenge everything we thought we knew, proving time isn't a universal constant but a flexible thread woven by gravity's hands. Yet for all we've uncovered, the deepest mysteries remain. What truly happens beyond the event horizon? Can information ever escape, or is it lost forever? And could we one day harness these terrifying time warps to peer into the distant future? The most thrilling part, these aren't just questions for physicists, they're puzzles we can all explore. Maybe you've got a wild theory about white holes or a burning curiosity about quantum entanglement near the singularity. Drop your thoughts in the comments below. What fascinates or terrifies you most about black hole time dilation? And if you're hungry for more cosmic mind benders, hit that subscribe button. From wormholes to dark energy, we're just getting started unraveling the universe's greatest mysteries. Until next time, keep looking up, because out there, at the edge of a black hole's shadow, time itself is waiting to surprise